Hello, welcome to this lecture on biomathematics. We have been discussing statistics as a theme for a few lectures, and we will continue discussing a little more about statistics in the coming lectures. So, today we are going to discuss two distributions, something about uniform distribution and Poisson distribution. So, the general topic is statistics, and first we are going to discuss something called uniform distribution. So, what is uniform distribution? We have heard of normal distribution, we heard of exponential distribution. So, what is uniform distribution? Uniform distribution, the name itself suggests that everything is same, uniform. Everything is equal, the probability is equal. So, this is essentially the probability distribution. So, previously we had exponential. If you have look at here, if you have x and p of x, we had exponential distribution which look something like this. We had normal distribution which looked like this. Now, what is uniform distribution? Uniform distribution would itself mean that it can't be, it has to be uniform everywhere. So, if I, what does it mean is that for any value of x, the p of x should be same like for all values of x. So, essentially uniform, this name itself would suggest something like this, uniforms everywhere the same. For this value the probability is same, for this value the probability is same. So, such distributions are called uniform distribution. We will come to this picture later, but let us look at some examples to begin with. Let us look at some examples in biology, or for generally examples that you see around that will have a uniform distribution. So, as we said, there has to be equal probability. So, any number of any set of events that are equally likely, that is equally probable, will have a uniform distribution. So, that is the key here, events that are equally likely. That means, if the probabilities are equal, then you will see a uniform distribution. So, the simplest thing you can imagine is results from tossing a coin. If you toss a coin, you will get either head or a tail. If it is head, as you know, you have only two events here. So, let us discuss the example of tossing a coin. Tossing a coin. So, there is only two outcomes, either head or tail. If you toss a coin, you will get the sign which we call one side of it, we can call it as head, and the other side can be called as tail. So, you will get either head or tail. So, that means you will get either one side or the other side. So, there are total two outcomes, either head, this is one, this is other one. There are two outcomes, head or tail. Now, both of them are equally probable. That means, half of the time it will be head, half of the time. So, probability of finding head or the first outcome is half, and probability of finding the second outcome is half. So, these are equally likely. So, this is equal probability, head and tail have equal probabilities. So, if you have a distribution of, if you have a histogram of head and tail. So, probability, this is head and this is tail. So, this probability of getting head will be half, and probability of getting tail also will be half. So, this is half. So, this is, we can call it uniform. So, this is an example of a uniform distribution. So, the next example that I discussed here is results from throwing a die. So, die is, you know what the die is? Die will have like 6 sides. So, if we play for playing people use dice. So, it will have 6 sides with 1, 2, 3, 4, 5, 6 either written or marked. So, there will be either 6 dots or 1 dot, 2 dots, 3 dots. So, you might have seen like dice like with one side having 1 dot, then another side having 2 dots, another side having 3 dots, another side having 4 dots, another side having 5 dots, and you can see a side having 6 dots. So, this is different sides of a die. So, now if you toss this die, if you throw this die, and when it falls down, if you look which one of this is the side that is coming up, you will see that there is equal probability for all of this to come. So, if you do it like many 1000 times, if you throw the dice 1000 times, so there are 6, let us write here total number of outcomes is 6. Total number of outcome is 6. So, each of them have equal probabilities. So, this has same probability. So, what does that mean? That means that if you have like 600 times if you throw this die, or if you throw this die, if you throw a die like let us say 6000 times, on an average at least 1000 times 1 will come, 1000 times 2 will come, some 1000 times 3 will come, 1000 times 4 will come, 1000 times 5 will come, 1000 times 6 will come. So, if you do this 6000 times and draw this graph, how many times you got 1, how many times you got 2, how many times you got 3, 4, 5 and 6. So, you would get like 1000 times 1, another 1000 times 2, 1000 times 3, 1000 times 4, 1000 times 5 and 1000 times 6. So, this is 1000. So, if you attempt 6000 attempts, if you throw the die 6000 times, on an average 1000 times you will get 1, 1000 times you will get 2, 1000 times you will get 3, 1000 times you will get 4, 1000 times you will get 5 and 1000 times you will get 6. So, this is, one can call it as uniform distribution. So, what is the probability of getting 1, 2, 3 or 5 or 6? So, out of 6000 times, out of the 6000 attempts, 1000 times you got one side. So, the probability is 1000 by 6000, because it has to be less than 1. So, it is like 1 by 6, or in other words, if there are 6 events possible or 6 outcomes possible. So, each outcome is the same possibility. So, 1 by 6, each of this 1 by 6. So, 6 into 1 by 6 is 1. So, the total probability is 1. So, this is called a uniform distribution. So, in other words, like you can say that P of x is some constant k. That is, it's like it's always the same. Now, what is k? Well, how do we find it? So, integral P of x dx has to be 1. So, the total number of probabilities, or sum over I P of x I has to be 1. So, is the total, if you using this condition, you will find that if there are n events, k is 1 by n. if there are n events, k is 1 by n. So, just like we found 1 by 6 or 1 by 2, there is total number of events or total number of outcomes, and if you divide 1 by the total number of outcomes will be the probability. So, P probability will be the total number of 1 by total number of events. So, if the distribution is uniform, this will be the probability. Okay. So, now the third example which we discussed is here. There are, let us say you have a random sequence. So, let us say n base pair of random sequence. So, let us think of 3 base pair. Let us think of random 3 base pair. So, like a codon of 3 base pair, a codon of 3 base pair. What is the probability that you will find a codon of ACT? What is the probability? So, to find this, first of all you have to know how many kinds of codons are possible. So, you can know that you can have A, it can be GAA, it can be TAA, it can be CAA. So, for each of this letter you calculate how many of them are possible, right. So, there is this you can change 4. Now, you can each of this A can be changed to, so this A can be changed to C, G or T. So, AAA you can change this to either AGA, AAA, ATA, ACA. This can be further divided, so on and so forth. So, you count the total number of possibilities, and if you find n, it will be like 1 over n will be the probability of having a 3 base pair of codon ACT. So, take this as assignment and find out what is the probability of finding a codon of ACT if all of the sequences were equally likely. So, the way to do this is write down all possible sequences with having 3, like all possible combinations of having 3 of them, and then 1 over that will be the probability. So, if you have n sequences, n different types of sequences possible for this codon, you will have 1 over n as a probability of finding any of this codon, because all of them are equally likely. So, that is the idea of uniform distribution. So, see here what is plotted. So, this is uniform distribution, the idea is plotted here, P of x versus x, and the P of x is a constant A here, and as we said, A can be some number which is something which is less than 1. It could be a fraction, A is a fraction essentially between 0 and 1. Okay. So, this is the uniform distribution. Now, we can ask little more complicated question. So, we found this, like if there are n events possible, it's like 1 over n is the probability. So, now let us say you are tossing a coin 2 times. So, if I toss a coin, like let us say you toss it 2 times, what is the probability that both times you get head, or what is the probability that both times you get tail? So, the answer is that. So, let us think about how many events are there. So, what do we are tossing a we are tossing a coin 2 times. So, if I do a 2 times tossing, this is like you might get like one head and the other one as tail. Now, you toss it 2 times, you might get the first one as tail and the second one as head. You ask your friend to toss it 2 times, your friend might get 2 tails. You ask somebody else to toss, so that person might get 2 heads. So, these are the 4 possible events. So, either when there is only one causing, there are only 2 events possible, a head or tail. So, then we found that the probability is half. Here there are 4 possible events like head and tail, because we are tossing it 2 times. So, if I toss it 2 times, I might get a head or tail, one H followed by T. If you ask this question, like what if you do this, you might sometime get the first one as tail and the second one as head. Somebody else might get T and somebody else might get H. So, in such cases, so we have 4 events and 4 of them, all the 4 are equally likely. So, the probability of getting 2 heads or 2 tails, probability of getting 2 heads, there are 4 events possible. So, like 1 by 4. This is just one event among the 4. So, there are 4 events and this is just one event among the 4. So, it is just 1 by 4. Now, you can ask the question, what is the probability of getting same toss, same side all the time, both the times. So, you are tossing it 2 times. How many times you will get both the time you will get the same side. So, here both the time you got like different sides, here also you got different sides, but here you got both the time same sides. Here also you got both the time same size. So, 2 out of 4 you got same side. So, the probability of getting same sides when you toss twice, that probability is 2 by 4, that is half. So, this is the probability of getting same side when tossing twice is half. So, just like counting like this, we can just learn something about these probabilities. So, I set an example of tossing a coin here. In a few minutes or in what follows sometime later, we will discuss something about cancer and mutations in cancer and all that. There we will use the same idea and find out something very interesting, the same kind of counting. So, what is the instead of just like instead of coin, we will talk about something else which is related to cancer. So, in a few moments, in something what follows, we will discuss how this idea of probabilities can be applied to understand something about cancer. Okay. So, we have uniform distribution. Now, we are going to discuss another distribution called Poisson distribution. Poisson distribution is distribution of random events. When you say something about random events, the immediate thing that comes into picture is mutations. So, mutation is something that you can immediately think of as a random event. So, something about mutations can be described by this Poisson distribution. Another day to day life, we can think of many examples that can happen randomly. Like one example that everybody might have seen is, let's say you go under a mango tree or something, or an apple tree, whatever tree you like, and you ask like randomly mangoes fall down. So, we will discuss something about randomly falling mangoes and how can that be described using Poisson distribution. So, first let us go to this mutation. So, look at here. So, let us say imagine that you have many copies of a DNA, each of length L. So, you have many copies of DNA in each of having length L. So, let us say like 1000 base pair of DNA. So, on an average, so let us say you have 1000 base pair of DNA. So, many copies, thousand base pair of DNA. There are many copies like this. Now, each of these copies have some mutations. So, let us say this has some number of mutations, this has some mutations, this has some mutation, this has some mutation. So, let us say that on an average there are 4 mutation, average number of mutations. Let us say there are 4 mutations on an average. So, some of them will have 3, some of them will have 1, some of them will have 5, some of them will have 10. So, on an average, let us imagine there are 4 mutations. So, now you randomly pick one DNA piece and ask the question, what is the probability that you will find a DNA with 3 mutations? So, if you ask this question, the answer to this question is given by this Poisson, by the distribution of Poisson statistics, the Poisson probability distribution. So, let me make this question a little more clear. You have a set of, you have many pieces of DNA, and each of this DNA has some number of mutations, and if you find out the mean number of your average number of mutations is 4. What does that mean? That means some of the DNA pieces have 3 mutations, some of them have 4 mutations, some of them have 5 mutations, some of them have 6 mutations, some of them have 2 mutations. So, there are many mutations, like, but on an average, the average number of mutations is average number of mutations per filament, per DNA piece is 4. So, now you randomly choose one DNA from a million pieces of DNA you have, or large number of pieces of DNA you have, and ask the question, what is the probability that, can you, before doing this, can we say what is the probability that you will pick a DNA that has 3 mutations? Okay. So, if you ask this question, the answer of this is given by something called Poisson distribution. So, that is what we are discussing, how likely that you will find a DNA with exactly 3 mutations. So, if the average number of mutations is 4 per copy, how likely that you will find a DNA with exactly 3 mutations? Okay. So, the answer is that the probability that you will find a DNA with 3 mutations, if the average number of mutations is 4, is given by this calculation, 4 power 3 into exponential minus 4 by 3 factorial. So, you can calculate this. So, this is how this comes, we will discuss later, but for the moment just realize that there is a formula, and this formula is known as the Poisson formula or the Poisson distribution, this probability distribution. So, let us generalize this. If we generalize this, what we get is that probability that you will find a DNA with exactly R mutations if the average number of mutations is m. So, probability that you will find R mutations if the average number of mutations is m. So, now you substitute m as, in the previous case, m as 4 and R as 3, you got the you can get the previous formula that we had used here, m as 4 and R as 3. So, P of R comma m is equal to m power r e power minus m divided by r factorial. You know, like 5 factorial is 1 into 2 into 3 into 4 into 5. 3 factorial is 1 into 2 into 3, like n factorial is 1 into 2 into 3 into multiply up to multiply 4, 5, 6, all this up to n. 1, 2, 3, 4, like let us say this is 8, so on up to n. So, you multiply n of them together, you get n factorial. So, this is the definition of r factor n factorial. So, the p of r comma m is m power r e power minus m by r factorial. So, probability that you will find a DNA with exactly r mutations. So, this is called the Poisson distribution. So, let us go back and think a bit more. So, if you have on an average 4, so what we have here is p of r comma m is, we saw that this is m power r e power minus m by r factorial. So, this is the probability of finding r mutations if you have on an average m mutations. So, let us say that on an average there is only one mutation. There is only one mutation on an average. That means, if you have some of them will have 2 mutations, some of them have 3 mutations, some of them will have 4 mutations, but many of them will have 0 mutations. So, the average mutation is only 3. Let us say the average mutation is only 3, then how does this plot would look like? So, sorry, the average m is 1, let us say m is 1, and how do we plot p of, let us say m is 1, we want to plot p of r comma 1 by 1. So, probability of finding anything above 1 will be less, because on an average it is 1. So, this looks something like this, something like this. So, only 1 you will find, but above 1 is like very likely to very less likely to find. So, we can plot for each m, we can plot p of r comma m, and for m is very large, it can look something like this. So, the shape of this curve will look like, will depend on the value of m. So, do plot this for different values of m and see what you get. For some intermediate value of m, which is 5 or 6, it might look something like this, 3, 4 and all that, you might look something like this. So, do plot this p of r comma m for different values of m and have a look at it and get a feeling how this will look like. Okay. So, this is the answer for the probability of mutations. Now, we can ask the question, what is the probability, we can think about now probability of getting mangoes. So, let us say that you are sitting under a mango tree and you see that mangoes fall down. So, now you wait for every day morning, you go and wait every day, at some point you go and wait for 1 hour near a mango tree and you see that some number of mangoes fall down. You do this, let us say the first day you waited for 1 hour and you got 3 mangoes. The next day you waited for 1 hour near the mango tree and you got 8 mangoes. The next day you waited near the mango tree and then got 10 mangoes, all of them falling down. You do not pluck the mangoes, you only take those mangoes which are fallen down. So, you find that first day 3 mangoes fell down, next day 7 mangoes fell down, the next day 10 mangoes fell down, the next day only 1 mango fell down, and like, so you just keep counting each day how many mangoes were falling down in the 1 hour period that you are waiting there, and you find that, let us say on an average 6 mangoes per hour fall down. If you wait for an hour, 6 mangoes fall down on an average. So, you sum over all these days and divide by the total number of days, you will get the average number of mangoes that you get in 1 hour time, and then let that be 6. So, now you can ask this question. So, let us say you did this for like about 100 days or many days and 30 days, and you caught this number, and then you can ask the 31st day, what is the probability that I will get 5 mangoes, or what is the probability that I will get 10 mangoes. So, this is again described by the Poisson distribution. So, what do we want? We want probability to get 10 mangoes when the average is 6. So, this is again the same formula we have to use that we described some time ago. So, the answer to this is 6 power 10 into e power minus 6 divided by 10 factorial. So, that is what here the probability. So, if you look at here the probability that you will get exactly 10 mangoes in 1 hour, if the average number of mangoes in 1 hour is 6. So, that is what this tells us. Now, this is probability of getting exactly 10 mangoes. So, now you can ask the question slightly differently. You can ask the question, what is the probability of getting 11 mangoes? So, you can ask the question, what is the probability of getting 11 mangoes? So, this is 6 power 11 e power minus 6 by 11 factorial. What is the probability of getting 12 mangoes, 13 mangoes, and so on and so forth. So, you can calculate all of this. If you know all of this, you can ask the questions, what is the probability of getting at least 10 mangoes? That means, sometime it can be 11 mangoes, sometime it can be 12 mangoes, sometime it can be 13 mangoes, at least 10 you should get. So, it is the sum of all these probabilities, because even if you 11 gets like it is at least 10. So, the probability of getting at least 10 mangoes is given here. So, if you look at the slide here, on an average 6 mangoes fall down every hour. How likely that you will get 10 or more mangoes in an hour? So, it is the sum over all this probabilities that we wrote down previously, like sum over r is equal to 10 to infinity, because you can get as many as mangoes as you want, and this is 6 power x by e power minus 6 by r factorial, and you sum over r. So, that is you sum over p of 10 6 plus p of 11 6 plus p of 12 6 plus dot dot dot. So, this is the probability that you will get at least 10 or greater mangoes. So, this is the probability of getting 10 or more mangoes. Is the sum, at least 10 is this, probability of exactly 10 is this, exactly 11 is this, exactly 12 is this, exactly 13, exactly 14, and so on and so forth. You sum up to infinity, you get the answer, probability of getting 10 or more mangoes. You can extend this to mutations. So, you can ask the question, what is the probability that you will find a DNA with at least 2 mutations? Probability that you will find a DNA with at least 2 mutations, if the average number of mutations is 3. So, and the answer to that is this, which is p is equal to sum over r is equal to 2 to infinity 3 power r e power minus 3 by r factorial. So, this is this answer. Okay. So, now we learned a few things about Poisson distribution, and now we will take a real biological example and a very famous example and discuss and find out how this idea, whatever we learned so far today, can be used to understand something about cancer. So, what I will discuss today is mutation and cancer, Dr. Knudson's study. So, Dr. Alfred Knudson was a well-known doctor in MD Anderson Hospital in Texas. So, he was a doctor treating patients with retinoblastoma. Retinoblastoma is a type of a cancer that comes for eyes, like so cancer tumor in eyes. So, that is called retinoblastoma. So, and he had some record data of his patients having retinoblastoma, very preliminary data, like he will write down what is it, just like any doctor would write down. Dr. Knudson from typical data from a doctor would be like what is the age and all that, and then which eye, like you have like both the eyes, one of those eyes will have cancer, maybe both the eyes will have cancer, this retinoblastoma. So, he will write down, and so this is the very simple information, like whether there is something called inheritance. Is it like your parents, did they have, if the patient's parents did have cancer, or those kind of very preliminary information he will write down. And he collected the data. The data is like, we will see the data in a different, at a different point, but at this moment is not important. At this moment is like very simple things, like, so so basically what we have to understand is that he had some data, very preliminary data that any doctor will get it, and using this data and some ideas of Poisson distributions and uniform distribution, he found some interesting, he reached some interesting conclusions, and he extended this later to form something called the famous two-hit hypothesis in cancer. So, we would not discuss the two-hit hypothesis today, but we will discuss some interesting conclusion that can reach by just knowing Poisson distribution and uniform distribution. So, what did Dr. Knudson have? So, Knudson had just a set of data, and he asked the question, the following question. He asked, if 95% of his patients, sorry, there is a spelling mistake here, like patients, like so there is a typo here. Okay, so if the 95% of the patients have retinoblastoma, that is at least one tumor, what should be the average number of tumors? So, he found that 95% of the people that came to him or came to this hospital had at least one tumor. That means they had some retinoblastoma, some cancer, at least one tumor, one growth in either of the eyes, like at least one tumor in total. If this is the case, what should be the average number of tumors? Like you should have like 3 tumors, 4 tumors, 5 tumors, or only just one tumor. So, the answer to this can be easily found from the Poisson distribution. So, the question he asked is that, let us say on an average, like you had like only one tumor or 2 tumors and 3 tumors. So, then you can ask the question. So, you can ask first you can assume that the tumor growth is a random process. So, because it is coming from mutation and so on. So, it has to be a random process. So, if it is a random process, it will have a Poisson distribution. So, if this has a if tumor probability of finding tumor is having Poisson distribution, or probability of tumor growth have Poisson distribution, then you can ask the question, probability that you will find a patient with exactly R tumors if the average number of tumors is m. If the probability that you will find a patient with exactly R tumors, if the average number of tumors is m, that is what we discussed so far, p of r comma m, which is m power r e power minus m by r factorial. But what Knudson wanted is that he doesn't know, he wants at least, he doesn't want exactly R tumors, he wants at least one tumor. So, what can he write down from this? He can write down probability of having one tumor if the average is m, probability of having two tumors if the average is m, probability of having three tumors if the average is m, so on and so forth. So, now we can sum of all this. So, now the probability that there is at least one tumor, probability that there is at least one tumor is given by p of 1 comma m plus p of 2 comma m plus p of 3 comma m dot dot dot. So, this is the probability that there is at least one tumor. That means, if a patient has, what is the probability that a patient will have at least one tumor is given by this sum. So, that is what described here. The probability that you will find a patient with at least one tumor if the average number of tumors is m, is sum over r is equal to 1 to infinity m power r e power minus m by r factorial. So, this is what we just described, and Knudson found that this is 0.95, that is 95% of the patients had at least one tumor. Some of them had more than one, but all of them had at least one. So, this is the probability of finding the patients with, that means if we had 100 patients, 5 patients did not have any tumor, 95% had at least one. So, if you want to get this, what should be the value of m for which this sum is 0.95? You can ask this question. So, you can do for this for different values of m. So, Knudson wrote a table for different values of m and r, and he did this sum, and he found that this is true only when m is equal to 3. This equation is true only when m is equal to 3. So, what does that mean? That means, if 95% of the patients have cancer, it means that there has to be on an average 3 tumors per person. So, just by asking a simple question, he could find out what is the average number of tumors. It is not 1, it is not 2, it is 3. So, if 95% of the patients have tumors, at least 3 tumors on an average has to be there. He hadn't measured the number of tumors in each person, but without doing a measurement, just from simple ideas of statistics, Knudson could infer that there has to be on an average 3 tumors. This is a very interesting conclusion that he is reaching. Now, the next question he asked is something about unilateral retinoblastoma versus bilateral retinoblastoma. So, what is this unilateral retinoblastoma? So, let us look at here. So, if only one eye has tumor, it is called unilateral retinoblastoma. If both the eyes have tumors, or at least one tumor in both the eyes, we call it bilateral retinoblastoma. So, you can ask the question, what is the probability of finding retinoblastoma in the left eye. So, you can ask the question, what is the probability that finding the retinoblastoma in the left eye? So, if somebody gets a retinoblastoma as a result of some kind of a mutation, then the probability that it will be on the left eye will be half, and the probability on the right eye will also be half, because equal probability. It can come on the left eye, or it can come on the left eye or on the right eye, we do not know. So, the equal probability, there is no particular preference for mutation. Like it can if you look a large sample of people, there is no reason why it is on the left or on the right. It can be on either. So, there is no particular preference. So, the probability that you find the retinoblastoma on the left eye is half, because there is only two possibilities. It can either come randomly on the right eye or on the left eye. So, there are two events that we discussed earlier. There are two outcomes, retinoblastoma on the left eye or retinoblastoma on the right eye. There are only two outcomes possible. In these two outcomes, like the equally probable. So, the probability to come on the left is half, and the probability to come on the right is also half. Okay. So, now just like we discussed about, so what can we have? We can have either retinoblastoma in the right eye or on the left eye, and this is the probability of half. Now, we can ask the question, if one has total of two tumors, what is the probability that both of that will be in the left eye? So, if somebody has two tumors in the eyes, you can have what are the different possible situations? The different possible situations is, like it can be on the right one on the right and one on the left, one on the right and one on the, both on the right, one on the left and one on the left, one on the first one will be on the left and the second will be on the right. So, there are four possibilities. So, the probability that you get on both of it on the left eye is just 1 among 4, is just 1 over 4. So, this is basically half into half. So, the half probability to get here, and the next one is half. The product of this is 1 by 4, and that is how you get, there are 4 events and this is only one of the 4 events. So, you get 1 over 4. So, if one has total of 2 tumors, what is the probability that both of that will be in the left eye is half into half, which is 1 by 4. Now, you can ask the question, if one has total of R tumors, what is the probability that all of that will be in the left eye? So, that is half power r, because half into half into half into half into r times half power r. So, what do we have? In the unilateral retinoblastoma, we have probability of finding R tumors in the left eye is half power r, probability of finding R tumors in the right eye is half power r. So, the total, like either in the left eye or in the right eye, is 2 times half power r, which is 2 into half. So, this is 2 into half power r. So, from this Knudson could find out, using this Knudson calculated the fraction of people having unilateral retinoblastoma and compared with this data, and again found that the average number of tumors is 3, because he could already calculate probability that there are R tumors when the average is 3. Then he could calculate what fraction of this is unilateral, that is half power r into 2. So, this is the fraction of people having unilateral retinoblastoma will be 2.5 per hour, just like we saw. So, from this he could conclude again that when m equal to 3, he found that the fraction of people having unilateral retinoblastoma also agreed with this m equal to 3 that he obtained. Okay. So, to summarize, we discussed uniform distribution and Poisson distribution, and we found that some examples of uniform distribution and Poisson distribution, and we at the end discussed an example where one can apply these simple ideas to get some insights about cancer, in this particular case of retinoblastoma, as Dr. Knudson did this in 70s. So, this is a famous paper by Knudson, and we will discuss this paper in little more detail, because he used the ideas of statistics and found out a few more things. So, that we will discuss in the coming lectures. So, today we will summarize just by saying that we discuss uniform distribution and Poisson distribution, and we will discuss more about statistics later. This is all today's lecture. Bye.